Euler's formula is often called one of the most beautiful equations in mathematics. At its heart, it shows how the exponential function, the imaginary unit, and trigonometric functions are linked by a deep and surprising harmony. Leonhard Euler, the Swiss mathematician who lived in the 18th century, discovered this connection while exploring infinite series and the nature of complex numbers. His insight changed how we understand waves, oscillations, and the complex plane. To grasp the magic of Euler's formula, consider its pieces. The number is the base of natural logarithms and describes continuous growth. The imaginary unit satisfies, extending the real numbers into the complex domain. The functions and describe rotations around a circle or the projection of a point moving on a unit circle. By linking these, Euler's formula says that exponentiating an imaginary number describes circular motion. The derivation of Euler's formula relies on the Taylor series expansions for, and the exponential function is expanded as. Replacing with and expanding gives a series with real and imaginary parts that match exactly the series for cosine and sine. It's a proof of how infinity, when handled with care, reveals structure instead of chaos. One famous result from Euler's formula is Euler's identity. This remarkable statement ties together 5 of the most important numbers in mathematics, 0, 1, and many consider this identity the most beautiful equation ever written, a symbol of how pure logic can reveal profound truths. Beyond its elegance, Euler's formula is incredibly useful. In electrical engineering, it describes alternating current and helps calculate phase differences using phasors. In quantum mechanics, it represents wave functions that describe the probabilistic nature of particles. In signal processing, it's the backbone of Fourier analysis, which decomposes complex signals into sums of sines and cosines, making modern communication possible. Visually, Euler's formula shows that multiplying by rotates a point in the complex plane by an angle. This bridges algebra and geometry and helps us understand rotations, oscillations, and waves in a unified way. It demonstrates that abstract concepts like imaginary numbers are not just theoretical curiosities but practical tools for solving real-world problems. Euler's formula shows the profound unity hidden beneath the surface of mathematics. It embodies the idea that different branches of math algebra, geometry, and analysis are not separate islands but parts of one great ocean of knowledge. For students and mathematicians alike, it remains a shining example of how a simple insight can illuminate vast areas of science and technology. In the end, Euler's formula is more than an equation. It is a bridge between numbers and shapes, between theory and application. It reminds us that within mathematics lies a hidden beauty, waiting for curious minds to uncover its secrets.